Hey guys, so this is going to be a video on section 11.3, just a little bit about the dot product. So first thing we should know is why do we want to do the dot product? Well, we know we can add vectors and subtract vectors, but what about multiplying? So this is another one of those operations with vectors, and it's a very special type of multiplication, let's say. And as we get more into multivariable, we'll see that vectors and discussing things with vectors is really the right language for discussing three-dimensional geometry. Okay, so the first thing you should know about the dot product is that, in a sense, we are multiplying two vectors to get a scalar. And remember, a scalar would be the same thing as like a constant. Okay, and let's just give a definition of how to calculate the dot product. So if I have a vector A, and I want to dot it with a vector B, that will be equal to the sum of each of their components multiplied. Now, I don't mean that you should multiply A1 with B1, B2, B3, so on and so forth. I mean that their corresponding components are being multiplied. So A1, B1 plus A2, B2, and so on and so forth up to the nth term, okay, A and Bn. And notice that this is a sum, so we will get some scalar or a number. This will be equal to a value by itself. Okay, but why is this useful? Okay, well, there's another definition or corollary with the dot product that says if I dot A with B, I will get the length of A times the length of B times cosine of the angle in between them. And let's see what that looks like a little bit. So if I have vector A and vector B, okay, then A dotted with B will be equal to the length of this segment times the length of this segment times the cosine of this angle. This is a really useful kind of corollary formula because this tells us about lengths and angles at once. And it's great because we have the lengths and the angles here, but this, if we use this definition up here, is really easy to calculate. So this part would be really easy to calculate and then figure out a missing part of this formula, okay? But why does this work? So we're gonna do a little proof. What does this mean? Okay, so let's just see first if I dotted A with itself. So if I did A dot A, that would be the length A times the length A. So we're gonna say length A squared times cosine of, well, let's think about this. If I have vector A and I am dotting it with itself exactly, then the angle between those two vectors is 0. And cosine of 0 is 1. Okay, so now we have that A dotted with A is equal to the length of A squared. Okay, and if we remember, length of A specifically will be equal to the square root of A1 squared, oop, dang it, not B1 squared, A2 squared, so on and so forth, AN squared, okay? And so if I see that, oh, we'll take a look. If we look back at our formula up here, this would be A1 squared, A2 squared, AN squared. And so if I square the length, I will get exactly what this formula said before. Okay, so yes, A dotted with A does in fact equal A1 squared plus A2 squared, so on and so forth, AN squared. So that checks out, good. Okay, but what if we have two different vectors, A dotted with B? Okay, well, this is where we're gonna use a little pre-calculus. So let's again draw A and B. We've got theta in between them, okay? So I want you to remember the law of cosines, and maybe that's a little far away. So I will remind you what the law of cosines says. So remember that the law of cosines says, it tells us about the length of a third side which we will call C, okay? And this angle right here. So let me write down the law of cosines. Law of cosine says that the length of vector C, I guess side C, but now we're dealing with vectors. Okay, length of side C is equal to the length of A squared plus the length of B squared. And if I stopped here, that would be the Pythagorean theorem. But remember that this is useful because we don't have a right angle right here. So to accommodate for that, we subtract 2 times length A, length B, cosine theta. Okay? And let's just define C really quick. So the vector C, if I wanted to figure out what the vector C would be, I could take vector A minus vector B. Okay, and if we think about that, if I go out vector A and I want to get vector C right here, I want to know the change. This is kind of that head to tail almost. But I could just subtract the components as well. I would need to go back, you know, how many, it goes down B, what's the change, basically, what we're trying to say. Okay, all right, so using both of these things, I want to put what we did up here and this law of cosines together. And I forgot something. This is supposed to be length of C squared. Okay, so let's put the length of C squared from part 1 is definitely equal to C dotted with itself. Okay, but if I use this part right here, C dotted with itself is the same thing as A minus B dotted with A minus B. Okay, and something we'll talk about in class, but a lot of the regular properties hold in dot products, a lot of the same properties we can use in like multiplication. So here, yes, we can indeed expand this by foiling or doing whatever you would like, whatever you call it. So I'm gonna get A dotted with A minus A dotted with B minus B dotted with A, and finally plus B dotted with B. Okay, and remember this is still equal to the length of C squared. All right, so from step 1 again, I know that A dotted with A is the length of A squared, and that B dotted with B is the length of B squared. Okay, and then commutative property also holds, so this means minus 2 A dotted with B. Okay, great. Well, take a look. We almost have the law of cosines right here. So remember that we have length of C squared, and at first we use this definition, but now I want to do length of C squared and use this definition. So on the left side of my equation, I'm going to put the law of cosines right here. So length A squared, oops, excuse my vector, okay, plus length B squared minus 2 length A, length B, cosine theta, and then equals this right side of my equation. So again, length A squared plus length B squared minus 2A dot B. Okay, so if we take a look and we do some basic math here, we can eliminate this part and this part. Okay, and we notice that negative 2 length A, length B, sorry, getting a little sloppy here at the end, is equal to negative 2 A dot B. Well, if you just divide by negative 2, you'll get that length A, length B, cosine theta is equal to A dot B, which is exactly what we geometrically said up here. So this is a nice little proof using the law of cosines of this formula. So if you accept the law of cosines as a rule, and we can look up a different proof for that, that helps us prove this. This also, in reverse, can help you prove the law of cosines. Depends on which you're using as your given, okay? But this is just a little bit more on the dot product.